All right, so to find an inverse, remember we should check if it even has, if it's even a one-to-one function. And this one's a rational function, which is, most of the ones I'm going to give you will have a one-to-one function, but for the sake of just practicing a graph, a small rational function, right? We just kind of did domain, right? So whatever makes your denominator 0, which would be 3, that's not part of your domain, but that's also where your vertical asymptote is going to be. So 1, 2, 3. That's where the vertical asymptote is. Since the degree of the numerator is the same as the denominator, your horizontal asymptote is at the division of the leading coefficient. So that means I'm going to have a horizontal asymptote at 2. Right? And then you have to determine if you will intersect that horizontal asymptote, which you can do that by just taking your entire function and setting it equal to that horizontal asymptote, which is 2. And I'll multiply, remember, to get it out of the denominator. That simplifies. I'm left with 2x minus 1. If I distribute this 2, it's going to be 2x minus 3. Now, the fact that these two are exactly the same, when I try to subtract either left to right or right to left, you can't even tell, right? When I write subtracting by 2x, you can't tell if I'm going left to right or right to left. But it doesn't matter because they will cancel and leave you with -1 is equal to -3, and that's not true. So that means we do not cross the vertical asymptote, the horizontal one, I mean. And then I just use test points. And always try to use nice numbers to make things easier for yourself. So I notice that 0 is on the right side of this vertical asymptote. And plugging in 0 here and here is going to be 1 divided by -3, which will be positive 1/3. So that means my point is going to be here. And I know this is what it wants to do. And then I can choose 4, which plugging in 4 here makes 8 minus 1 is 7. 4 here makes 1. So that's going to be 7, which means it's going to be further up here. I just know it's above the horizontal asymptote. And since I don't cross the horizontal asymptote, I know it's going to look like that. Meaning this does pass the horizontal line test. Do I expect you to do this? No. I just want to do a quick review on vertical asymptotes. But I'll give you something that's a one-to-one function. And then you change your f of x to y. 2x minus 1 over x minus 3. And then this is the biggest step, right? Where all your y's become x's. And all your x's become y's. Oops. Y. And same like the previous one. To get something out of the denominator, I'm going to multiply by it. And the operations I notice is distribution. These two simplify. I'm left with xy minus 3x equals 2y minus 1. Now, I need to get my y's on the same side. So it doesn't matter if you want them on the left or if you want them on the right. I know there's an x here, but I'm only worried about the y. Just treat like that x like it was some other coefficient. So I'm going to subtract 2y to both sides. That's going to move and make it xy minus 2y. And if you want, either at the same time or if you want to do it in two separate steps, you can then add the 3x to both sides. Cancels on the left. And then you're left with -1 plus 3x on the right. And now you might be asking, what do I do from here? Remember, the trick is, since both terms have the same factor, you can use your GCF to take it out, and I can divide both sides by x minus 2. That's going to give me y is equal to negative 1 plus 3x all over x minus 2. And then you would just change your notation to say f inverse of x. So that y becomes f inverse of x. Now the next one. Well, this is a cube, right? So I know this looks something like that eventually, right? I know this shrinks it, so it might look wider, but it still passes the horizontal line test. These I can do a little bit quicker, right? From the previous one, right? I know pass, 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 fail, fail. Now this one fails, but remember we talked about that example where you can actually get rid of half of it, and then it will pass, right? But you have to restrict its domain. But we don't have to worry about that with this one. And I'll give you something you don't have to worry about. But here, we change our g of x to y. We have the cube root of 3x plus 2. And then I change all my x's to y's and all my y's to x's. So that's going to be 3y plus 2. So let's subtract 2 on both sides. X minus 2. And then it's going to be the cube root of 3y plus 2. Now, how do I get y out of that cube root? I use the power of 3. Right? And they work interchangeably, right? If, for example, if I had an x cubed and I wanted to get rid of the power, I would use a cube root to simplify the cube. And vice versa. I use a cube to simplify a cube root. And that's true for x squared as well. I can use a square root to simplify a square, or I can use a square to simplify a square root. Right? They go hand in hand with each other. So this helps me simplify the cube root. That leaves me with x minus 2 cubed is equal to 3y plus 2. I subtract 2 to both sides. And then x minus 2 cubed minus 2 is equal to 3y. And then I divide both sides, the entire side, by 3. And that leaves me with y is equal to x minus 2 cubed minus 2 over 3, which I rewrite as g inverse of x is equal to x minus 2 cubed minus 2 over 3. Ta-da. All right, with this example, remember, for transformations, the exponent, for exponentials, the exponent is the inside. Anything at the base of the level is the outside. Now, you have to be careful with the inside, right? Because now we are putting numbers in front of the x. Because whenever you see anything other than 1, whether it be negative or a 2 or a half, you want to make sure you factor that number out of both terms, because it is impacting this constant here. But right now, there's nothing there. What's the parent function? Well, it's just 2 to the x. So the base is bigger than 1. So I know I'm dealing with my horizontal asymptote is right here. Right? And the point, they all pass that. Remember what I said? They have that horizontal asymptote, and they all pass that 0, 1 point. But because the base is bigger than 1, I know it's going to go in this direction. And what changes as this gets bigger? 2, 3, 4, 5. It just goes faster. So 2 to the x, 3 to the x, 4 to the x, 5 to the x. That's the only thing that's changing. It just keeps going up quicker. But now that -3, remember everything inside happens opposite of what you think. So that -3 actually moves it to the right by 3. So it's going to be over here now. Now it doesn't change anything for your horizontal asymptote. That's still in the same place because moving 3 to the right doesn't change much, right? The only time it is going to move is I look outside to see if there's anything, transformations. This here is not outside. This is part of the function. It's what makes it an exponential, a base. But this 2 moves the whole graph up, which means you're going to also have to move your horizontal asymptote up by 2. And then the point will also move up 2 with it. Instead of being here, it is now there because it goes up. It was here before, 1, 2. But it still has the same overall shape. Now, I've said this before, and I'll say it again. If you want a more precise graph, you can always just make your table and choose X values, get your Y's, and you'll have a more precise graph if you ever need it, right? That table should always be in your back pocket, ready to use. But that's it. It just moved right and went up. The cube root. Here we go. Remember what I just said? They're all the same. Right? The cube root, 0, 0, 1, 1. So this is the parent function. And it's going to look like this. And I just do a quick rough sketch. This 3 moves it to the left by 3. So it's going to move here and here. There's 1, 2, 3, 1, 2, 3. And it has the exact same shape. So I try not doing them all on the same one, but sometimes it's good to do at least a couple so you can see the transition. Now this next one is outside, but there's 2 things going on here. The negative is going to cause a reflection, so it's going to do this and that. But the 2, it does everything you think. It's going to stretch this by 2. And it's doing it vertically because everything outside is vertical. Everything inside is horizontal. So whatever happens to the X is horizontal. What's happening to the Y is vertical. Now, the benefit is we do know this point here. The X is what moved to the left by 3. But it's still right here at 1. So I know that this point, I can do this in 1 step or 2 steps. I can reflect it, or I can just multiply that 1 by -2, leaving me with the point being, right now, the X is -2, but the Y is going to go down to -2 as well. So it's going to be right here at -2. But this one is still, this one's still at 0, right? Because this value here is -3 and 0. If I multiply 0 by -2, that doesn't change anything. But you can see how it gets, how it's stretched vertically. And well, this is where it was before, and it's getting stretched and reflected at the same time. So you can see how it gets wider and reflected. And it's doing the same thing on the other side. Remember, I'm not looking what's happening above, but I try to keep a similar shape. All right, because they're not symmetric. Obviously, they're not the same, but they have the same curvature. This one isn't going to all of a sudden still be down here, right? It has to have the same, kind of like a parabola, right? They all have an absolute value. It's not just like one all of a sudden gets flat and then the other one looks completely different. Like they gradually open and close at the same time. And then lastly, this 3, you move the whole graph up by 3. So it looks like this. The point up 3, this point up 3. So 1, 2, 3, 1, 2, 3. And we curve. Curve it. And we curve it. So 1, 2, 3. And the parent function was the cube part. So 1, 2, 3, 4. Absolute value. Again, all of these are the exact same example. Because I could easily just change. I can put parentheses and put a square. I could put a square root instead, right? Like they're all the same exact idea. And that's because they all share these 2 points. Because they share those points is what kind of allows us to do the same graph each time. So remember, the absolute value looks like a perfect V. Perfect diagonal on the left, perfect diagonal on the right. Have that same diagonal like slope. All right, looks like a perfect 45-degree angle. Obviously, the graph continues forever. Now, this is the part where I said there is a coefficient and a constant at the same time. So you can either handle it now or do it after the stretching and shrinking, because this one's a little tricky because you have to factor the 1/3 is not coming out of the absolute value. It's just coming out of the 2 terms. It's going to be x plus 1. And it's tricky because if it was like 2x plus 4, oh yeah, they both share a 2. But how does 1 share a 1/3? Right? There is 1 does not have a factor of a 1/3. So to be able to factor something that doesn't necessarily have that factor, the trick that I do is I just divide by whatever I'm trying to factor. And when you divide by a fraction, you can rewrite it. You have to multiply by the reciprocal. So that 1 over 1/3 is like 1 times 3 over 1, which becomes 3. So you can think about this as it becomes 3, right? I show the work here on the side. And the reason for that is, if you notice right away, you might think, oh, this is going to move 1 to the left. But it's actually supposed to move 3 to the left. But I have to take care of this 1/3 first. And again, the stretching and shrinking is the trickiest part when it comes to transforming. Left, right, up, down, reflecting is not too bad. But stretching, especially by a fraction, is really tricky. Because everything inside happens opposite of what you think. So you would think 1/3 is horizontally shrinking it, but it's actually horizontally stretching it, because it's the opposite of what you would think. Now, when I look at a fraction multiplying, to make it nicer for myself, I think about this as like x over 3. Because to me, now I'm saying, oh, I'm dividing x by 3. And the opposite of division is multiplication. And that helps me when it comes to this point. Right? Because these are 0, 0s and 1, 1s. Now, multiplying the x by 3 with the origin does nothing. But it does do something when I take this 1 and I multiply it by 3. Because then it changes it to three here. 1, 2, 3. So this becomes 3, 1, and you can see how it stretched horizontally, right? And I want to do that same sort of stretch on the left side. So I look at it as in like, okay, it's over 3. So this one, I'm kind of doing it over 3 as well. I kind of try to match it to be symmetric on both sides. But once you can do that stretching and you have those 2 points where you need them, now the next step, because we already did this factoring out, it looks like this. 1/3 x plus 3 minus 3. So I can take care of that 3 that moves this graph to the left by 2. Now I'm going to move my x and y axis, or my y axis, to the right a little bit. Since I'm moving this so far to the left, I don't want to make the x-axis, the y-axis right in the middle, because it's going to clash with this graph. But it moves 3 units to the left, so it's here. So the origin moved over 1, 2, 3. And then this one's moving over 1, 2, 3. It's going to be right at the y-axis. And it still has that same stretch shape. Same thing on the left. It's still going to have that same stretched shape. Oop, that's kind of curvy. Oops. This one's really extended. Let's keep it a little bit closer so it doesn't look exaggerated. And then the last part is just the 3, right? That just moves the graph down by 3. That's not too bad. I just follow the points. The origin goes down 3. That point just goes down 1, 2, 3. And I'm right here. Same shape. Same stretch. And there is my graph for these. For this one, I was supposed to put a parentheses around that one. Because if not, it would look like that. 4 adds with this -2. But remember, this is a logarithm with a base of 2. So what did we say all logarithms share? They have that vertical asymptote. And they share that point 0, 1. And since it's bigger than 1, it does, and that's the one we mainly focused on. It does this. Now, as it gets bigger, as the base gets bigger, all that changes is that this gets lower, lower, and lower. Now, if this was a fraction, it would go this way. So it's kind of like a reflection, sort of. But we're focusing on that. Remember, this point is 1, 0. Now, same thing as the previous one, right? If you want to do it at the beginning, you can, which is log base 2 of, I want to factor that 2. In this one, it's nice because I know 4 has a factor of 2. I can take it out because that tells me that the graph is going to move to the left by 2, not by 4. So once again, this says this is dividing, the opposite of division is multiplication. This one is multiplying, the opposite of multiplication is division. Because remember, inside always does opposite of what you think. So instead of multiplying your x by 2, you're actually going to divide it by 2. So it's getting shrinking horizontally. So it should look a little bit wider like this. Again, and I'm doing a rough sketch, so it's not going to always be perfect. But again, it's just a little bit wider because it's getting, it's shrinking horizontally, not stretching, sorry. It shrinks it. So it's kind of like pushing this here. So it pushes this up a little bit when it comes to the stretch. But once you take care of that, you just have to worry about this factoring out. And that 2 moves it to the left. But you have to watch out for your asymptote. Because you're moving to the left, the asymptote also has to move 2 to the left. And your point is going to be here. Because it was at a half, so it moves over 1, 2. So 1, 2 at this half. And it still keeps that horizontal shrink shape. There it is. So that moved to the left. And lastly, this moves it down by 2. So that will look, that point is moving down. The asymptote doesn't change because going up and down doesn't do anything to it. And then it still has that horizontal shrinking shape. I have to adjust it a bit, but there it is. Just goes down. So this looks like it moved to the left, but it's a shrink. Then it moved to the left, and then it shifted down. Now with these, you can either rewrite these, right? Remember the property I've always said, log base b of x is the same as b to the y equals x. So you can either rewrite them, or some of these you can remember those properties that said if your base and your argument are the same, it's equal to 1. So this is equal to 1. This one is similar. You can either rewrite it, but don't forget that ln means log base e of square root of e. So the base and the argument are almost the same. We just have to think about this square root that could be rewritten as ln of e to the 1/2 power, right? Because you can rewrite any radical as a rational exponent and vice versa. So that allows me to use this property that says when your base and your argument are the same, you can take your exponent and it equals it, right? Or for the natural log, it looked kind of like this. So that means this is going to be equal to 1/2. Now this one's tricky because there's nothing matching, right? So maybe for this one, I do want to resort to rewriting it as what power do I need to get 1/2? That's tricky because I know how to get 4 to become a 2 with a square root, right? 1/2 becomes a square root. But I need that 2 to be in the denominator. So that means I would need this to become a negative 1/2. Because that would look, I can rewrite that as 1 over 4 to the 1/2, which is 1 over square root of 4, which is 1 over 2, which is exactly what I'm looking for. So it's a little creative. You have to put a little bit of thought to it, but you can always resort to rewriting it and think about what it is. Same thing with this one. It's the common log. Don't forget, this means log base 10 of 1 over 1,000. But we don't write the 10 there because it's a common log. So when you rewrite it, just know that the base is 10. I'm trying to find the output to equal 1 over 1,000. Now I know how to get 10 to become 1,000 by just putting it to the power of 3. Because 10 times 10 is 100, and 100 times 10 is 1,000. But to put that 1,000 in the denominator, I'd have to put a negative in front. Right? Because that makes it 1 over 10 to the third, and that makes it 1 over 1,000. So either remember these quick formulas, or don't forget how to rewrite it into exponential form. Now we did a similar example of this a second ago, right? Where x at -3 is where my vertical asymptote is going to be for this one. So at -3, I have this vertical asymptote. And because the degree of the denominator is bigger than the numerator, I also know I have a horizontal asymptote at y equals 0. Now for the test points, I have to choose numbers. Well, one, I have to check if I actually intersect this graph, which we did on the previous example, which we set it equal to our horizontal asymptote, which when I multiply this to both sides, they simplify. That becomes 0, and 4 is not equal to 0, meaning I will not cross this horizontal asymptote. Now I have this 0 here. I could plug in. That's going to then give me 0 plus 3 is 3. And then it's going to be 3 squared is 9. So it'll be -4 over 9, which is less than 1, which tells me I am below that horizontal asymptote, meaning my graph is going to look something like this. And then on this side, I'll just choose -4, which -4 in here is going to give me -1, but -1 squared is 1. And then -4 divided by 4 is going to be negative. So right here I got -4/9, which is below this horizontal asymptote. Now I'm going to have -4, which is also below the horizontal asymptote. So at -3, I get -4. So once again, it looks something like this. So that's my graph. Now, these that get a little bit bigger, I can tell my horizontal asymptote already because these two are the same. I divide my leading coefficients. My horizontal asymptote's at 0 again. You have to check for intersection though, right? X squared minus 4 over x squared minus 4x equals 0. I multiply that x squared, 4x to both sides. Right? Cancels here. That becomes 0. Is that right? Oh, I made a mistake. That's what I get for rushing it. My horizontal asymptote is not 0. It is 1. Sorry for rushing it. Since they're the same, 1 and 1, that means that I would set this equal to 1, not 0. To 1. So when I multiply x squared minus 4x, x squared minus 4x, on the right, on the left it simplifies. On the right, it's x squared minus 4x. Which, same as before, these will cancel out eventually. And then I'm left with -4 equals -4x. And I divide by -4 to both sides. I get x is equal to +1. So that means I actually found an x coordinate and my y coordinate is 1. I found a point where my graph will cross the horizontal asymptote. Now, how do I find my vertical asymptotes? I have to take this x squared minus 4x, set it equal to 0. Now, we know it's a quadratic, and we usually use a diamond, but I'm going to take the GCF out, make it x minus 4. And this gives me x equals 0. This one's going to give me x equals 4. And those are going to be my two vertical asymptotes. Then I'll sketch both of them. And then I'll use test points to graph it. But I don't want to rush this, so I'm going to stop the video here, and I'll continue finishing this graph, and then graphing this P over Q, and then doing composition and checking inverses, which is also composition. And then doing more of these polynomial graphs, right? Either these are through factoring, and it's already factored for us. Oh, copying the same thing over and over again. But I'll continue another video to not make this super long.